Welcome. In this video we're going to look at a couple friction example problems. The first one we're going to look at is friction on an incline. So I've drawn the incline for us, and our textbook tells us that the coefficient of static friction between waxed skis and snow is 0.1, and the coefficient of kinetic friction between waxed skis and snow is 0.05. So the first question we're going to ask is, what is the minimum angle of the slope that we need in order to start sliding given the coefficient of static friction? Step number one, as always, is to draw a free body diagram. I'm going to draw our skier as a block because I'm not a good artist. So we need to draw the forces acting on our block, and as always we have mg going straight down. We have the normal force going perpendicular to the incline, and we're going to have this time a static friction force going up the incline, preventing the skier from moving. So we want to solve for theta here. And the key here is, at the instant the skier starts to move, we are going to go ahead and say the sum of the forces in the x direction is still 0. And the sum of the forces in the y direction is also 0. All right? After the skier starts moving, all bets are off. Not only that, but after the skier starts moving, it is then the coefficient of kinetic friction that takes over. And we can ask another question, and we will. What is the acceleration of the skier once they start moving? All right? So first up, we've drawn our free body diagram, and we remember that when we do inclined plane problems, we have changed our coordinate system so that the x-axis is parallel with the ramp, the y-axis is perpendicular to the ramp. So with that in mind, the normal force is going straight in the positive y direction. The frictional force, the static friction force, is going straight in the negative x direction. So we have two components of the weight, one in the x direction and one in the y direction. So this is going to be theta in here, and our y coefficient is going to be mg cos theta, and our x coefficient here, our x, oh boy, what do you call that? The vector component, that's it. Our x component is going to be mg sine theta. All right, so sum of the forces in the x direction is 0. So the forces acting in the x direction, let's see, we've got mg sine theta, and we have the static friction going in the negative direction. Those are equal to 0. In the y direction, we have the normal force going positive, and we have mg cos theta going in the negative direction. So we subtract it. All right, so we're solving for theta, and we have a theta in both our x equation and a theta in our y equation. And as you'll notice, the mass of the skier is not given. Anytime the mass is not given on an inclined plane problem, we're going to hope it cancels out. Okay? So we can drill down our frictional force here. We know that frictional forces are equal to the coefficient of friction times the normal force. So let's rewrite our x equation as mg sine theta minus the coefficient of static friction times the normal force. And over here in the y, we can solve this equation for the normal force. It's just equal to mg cos theta. So substituting mg cos theta in for the normal force, we end up with mg sine theta minus the coefficient of static friction times mg cos theta equals 0. So reminding ourselves again, we're solving for theta here. So let's go ahead and move the mu mg cos theta over to the other side. So we've got mg sine theta on the left of the equal sign. We have mu sub s mg cos theta over on the right. And here's where we see we've got a m on both sides. We also have a g on both sides. It's actually kind of curious that we would find the same result on the moon that we would on Earth in this same situation if we were able to ski on the moon. All right, our answer here does not depend on the mass of the object, and our answer does not depend on the acceleration due to gravity. Okay, so here we've got sine theta equals mu sub s cosine theta. So let's divide both sides by cosine theta, giving us a sine theta over cos theta equals mu sub s. Sine theta over cos theta we know is tangent of theta. So the tangent of theta is equal to mu. And we are going to take the inverse tangent of both sides, and we end up with theta is equal to the inverse tangent of the coefficient of static friction. That result is actually worth remembering. It's a very easy equation to remember. The coefficient of friction and theta are related to each other here based on the inverse tangent. And we can use that result anytime we're looking for an angle at which something just starts to slide. So if we plug our numbers in, we have theta is equal to the inverse tangent of 0.1. And putting that in the calculator, let's see what we get. I get an angle theta equals 5.7 degrees. So that is not a very steep slope. And it makes sense because when we look back at the coefficient of static friction, 0.1, that is a pretty low coefficient of static friction. We are talking about skis on snow, waxed skis on snow, actually. And so it makes sense that our theta would be pretty small. So now the next question we ask, okay, we start to slide on this 5.7 degree slope. And the minute we start to slide, we recognize the fact that this coefficient of friction is no longer 0.1, it is now 0.05. So we are going to have some acceleration down the slope. So the next question is, based on this coefficient of kinetic friction and the angle we just found, 5.7 degrees, what is the acceleration of the skier down this bunny slope? Then it would be the bunny slope at 5.7 degrees. So now let's do that new problem. So our problems here are identical with one major exception. And that major exception is now the sum of the forces in the x direction is not going to be 0. The sum of the forces is going to be ma. So we're going to set it up. We're not necessarily going to solve it, but we're going to show how we would go about solving it. So we've got, again, mg going down. We have the normal force going up. And we have, this time, kinetic friction going back up the ramp. And I have no idea where that big black line just came from. Where did you come from? Get out of there! Okay, mg, normal force, kinetic friction going up the ramp. All right, so we have the sum of the forces acting in x this time is equal to ma. The sum of the forces acting in the y direction is still equal to 0 because this skier is not accelerating perpendicular to our incline. So the sum of the forces acting in x, again, we've got to remember that our weight force is in two components, and those components are the same as they were in the last problem. So the x component is going to be mg sine theta. And we've got the force of kinetic friction equaling the mass of the skier times the acceleration. And over here in the y direction, we have mg cos theta going down and the normal force going up. Let's do a negative sign here. Normal force minus mg cos theta is equal to 0. Oh, lovely black lines again. Thank you, Promethean. All right, so let's see here. We need to substitute in our equation for the force of kinetic friction. So we have mg sine theta minus the coefficient of kinetic friction times the normal force is equal to ma. And again, the normal force from our y equation is going to be mg cos theta on that side. So substituting mg cos theta in for our normal force, we've got mg sine theta minus the coefficient of kinetic friction times mg cos theta is equal to ma. And we see again, hey, we didn't know the mass of the skier, but mass cancels out because we have a mass in every single term on both sides of the equal sign. Notice that g does not cancel out this time. The acceleration down the ramp does depend on the acceleration due to gravity, as should be obvious. So since we know g, we know theta, we know mu sub k, we can plug everything in and solve for the acceleration down the ramp. All right? Next, we're going to take a look at a system of masses problem. Okay, friction and systems of masses. Here is our setup. We've got M1 sitting on a tabletop with friction, and M1 has a mass of 10 kilograms. We have a coefficient of static friction between M1 and the table of 0.6. The question that we could ask here is, what is the minimum mass for M2 for this system to move? Okay, so we want to find out what M2 is going to be. And again, we're going to be looking at the sum of the forces acting is equal to 0 at that instant before it starts to move. Okay, and we're going to be solving for M2. So let's see here. We need to define a coordinate system, and let's go ahead and say that anything acting in those directions is positive. Anything acting in the other direction is going to be negative. So our free body diagram for M1 is going to be M1G going down, the normal force on 1 going up, and we have a force of static friction going to the left, and there's tension in the rope pulling M1 to the right. For M2, it's a simpler picture. We've just got M2G going down, and we have that same tensional force going up. All right. So as I've told you before, my trick for solving these types of problems is, let's just imagine this as a block resting on a table, and we've got forces that make it want to move in the positive direction. We have forces that make it want to move in the negative direction. Doing it this way cancels out those two tension forces since they're equal and opposite. So all we have to worry about here in our free body diagram is we've got M2G making the system want to move in the positive direction, and we have the force of static friction making the system want to move in the negative direction. Static friction. All right, so remembering here the sum of the forces on the system is 0. We've got M2G going in our defined positive direction minus the force of static friction, and that's equal to 0. Plugging in our equation for the force of static friction, we've got M2G minus the coefficient of static friction times the normal force on block 1 is equal to 0. Here's where our free body diagram from block 1 does come in. As we see up here, the normal force has to be equal and opposite to the weight of M1 because M1's not accelerating in the y direction. So we can substitute in the normal force on that block is equal to the weight of the block, M1G. So plugging that in, substituting for the normal force, we've got M2G minus the coefficient of static friction times M1G is equal to 0. Keeping in mind we're solving for M2 here, so adding mu M1G to the other side, we've got M2G is equal to mu M1G. We see that the acceleration due to gravity cancels out on both sides, as it did in the inclined plane problem, and we end up with the minimum mass for M2 is going to equal the coefficient of static friction times M1. Plugging in the numbers that we were given initially, the coefficient of static friction was 0.6, and the mass M1 was 10 kilograms. So we end up with M2 has to be at least 6 kilograms to get the system to move. Any less than that, the system stays static. Any greater than that, and the system is going to accelerate in the positive direction. And with either one of those cases, we could say if M2 was a mass of 4 kilograms, find the tension in the rope. Find the force of static friction on M1. If M2 was 8 kilograms, then I'd have to give you a coefficient of kinetic friction, but you could then solve for the acceleration in the system. You could solve for the tension in the ropes. All right, so all sorts of stuff we can solve for after this. But remember, or know, or recognize that our basic steps for solving these types of problems are still the same. We draw a free body diagram. We think about the motion of the system in terms of the sum of the forces. If the system is at rest or moving with a constant velocity, the sum of the forces is 0. If the system is accelerating, the sum of the forces is going to be ma. We plug in our forces and we solve for the unknown. That's the way we've been doing these force problems every single time. All right? And nothing has changed. We've just added a layer of complexity with static friction and kinetic friction. All right? I'll see you later.